neutrality is maintained. What we see here? We see this type of defect arises when some ion is missing from its lattice point and occupy the interstitial site. An ion is missing from its lattice point and occupy the interstitial site, then it is termed as Frankel defect. It creates a vacancy, here vacancy, and the interstitial defect. Together we call it as dislocation defect. The next, this is known as dislocation defect. It occurs in the ionic solid, as we have seen, in which the anion is larger, anion will be greater, so that it has greater interstitial site, and cation is smaller, so that it can easily accommodate the interstitial site. The next, it occurs in the solids such as silver chloride, silver bromide, silver iodide, zinc sulfide. So the next, in this defect, the electrical neutrality is maintained, as I have told you. We will discuss the next defect, that is known as Schottky defect. We have discussed this defect arises in ionic solid. Ionic solid. Let us see what happens in this type of defect. They have ideal arrangement of atoms in three-dimensional space. For example, let us see. This is ionic. This is the ideal arrangement of crystalline solids, but in this defect, equal number of cation and anions are missing from the lattice site. Let us see here. It means if in a defect equal number of cations and anions are missing from their lattice point, then this defect is known as Schottky defect. We see equal number of cations and anions are missing, then in that case the electrical neutrality is maintained. To the next, they are missed from the lattice, it means there is decrease in the density of the substances. What we see to the next, this type of defect occur in those solids which have the cation and anion of relatively similar sizes, as in case of AgBr. In case of sodium chloride, this type of defect occurs. What we know, first is that this type of defect arises when equal number of cation and anion is missing from their lattice point. The next, in this defect, equal number of anion and cation are missed. Therefore, they maintain the electrical neutrality. To the next, what we see, the atoms or the ions are missed from the lattice point. It means this defect leads to decrease in the density of substance. To the next, we have discussed that this type of defect occurs in those lattices which have the anion and cation of relatively similar sizes. It means this defect arises in those ionic solids which have anion and cation of similar size. For example, in case of NaCl, AgBr. Clear? To the next, potassium chloride, cesium chloride. It means Schottky defect, what we discussed, that this defect arises in ionic solid, maintain the electrical neutrality, occur in those solids having the cation and anion are similar sizes, does not affect the density of the substances, and it occurs in case of sodium chloride, silver bromide, potassium chloride and cesium chloride. Let us discuss the next defect that is known as impurity defect. Impurity defect. This defect arises due to presence of impurity during the crystallization of the substances. It occurs in ionic solids. For example, in case of sodium chloride, in case of silver chloride, let us see how it is happening. If during the crystallization of sodium chloride, some SrCl2 is present, and when it crystallizes, let us see what is happening. It means, what is the lattice? That is, this one is sodium. This one is sodium, Na plus Cl minus, Na plus Cl minus, Na plus Cl minus, Cl minus, Na plus 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 Cl minus, Cl minus, Na plus Cl minus, Na plus Cl minus, Na plus. This is the ideal arrangement of atom in the three-dimensional space. But what happens during crystallization? If it contains certain impurity of SrCl2. You know, Sr is divalent, plus 2. Then in that case, this Sr is going to replace 2 sodium ion. It means 1 and the next one is 2. And here, what occupies? Sr2 plus. If this type of defect occurs in a crystal, then it is termed as impurity defect because of presence of SrCl2. The sides of two sides Sr is divalent, therefore it is going to displace two univalent ion, that is sodium ion. What we see, the number of vacancy created by Sr is equals to the number of Sr atom. As we have one Sr atom, then it will create one vacancy. What we know? This type of defect arises when some ionic solid contain impurity during their crystallization. For example, when sodium chloride crystallizes containing some impurities of SrCl2, then in that case certain sodium ions are displaced by Sr2 plus ion. This is known as impurity. This is known as impurity defect. The next point is that the number of vacancy created is equals to the number of Sr2 plus ion. It means as Sr2 plus is divalent and displaces monovalent ion, therefore the number of vacancy created is equal to the number of Sr2 plus ion. The next one, in this defect, what we see, when two sodium plus are displaced, then one Sr2 plus is included. It means in this defect, the electrical neutrality is maintained. In this defect, electrical neutrality is maintained. To the next, what we see, for example, when cesium chloride, when cesium chloride, cadmium chloride, CdCl2 is impurity in silver chloride, AgCl crystal. This is all about the impurity defect. This defect arises due to presence of impurity in a ionic solid. During their crystallization, the cation is going to occupy the position of cation. The difference is only that if a divalent cation is going to occupy the position of monovalent cation, then it leaves equal number of vacancy. In this defect, the electrical neutrality is maintained, and we have another example of cadmium chloride impurity in silver chloride crystal. Let us discuss non-cytometric defect. Non-cytometric defect. In this defect, we have discussed non-cytometric defect. The elemental ratio is not maintained. The cytometric defect which we have discussed, it is not going to disturb the proportion of different element in a compound, but this is non-cytometric. It means this is going to disturb the proportion of element in a compound. It means in this type of defect, the proportion of various element in a compound is disturbed. Non-cytometric defect, as we have discussed, it is of two types. Metal excess defect. It is of two types. The first one is metal excess defect, and the next one is metal deficiency defect. Metal excess defect is of two types. The first one is metal excess defect due to anionic vacancy, and the next one, the metal excess defect. The metal excess defect due to presence of extra cation. Let us discuss them one by one. The first one, we will discuss the first one, metal excess defect due to this one, metal excess defect due to anionic vacancy. Metal excess defect due to anionic vacancy. Metal excess defect due to anionic vacancy. Let us discuss. It occurs in the case of lithium chloride, LiCl. The next one is NaCl. The next one is KCl. The color of sodium chloride is yellow. KCl is violet and LiCl is pink. What it means? When defect arises in lithium chloride crystal, then it develops pink color. When defect arises in sodium chloride crystal, then it develops yellow color. When defect arises in potassium chloride, then it develops violet color. So the next, let us see by taking an example of sodium chloride. What happens when we have a lattice of sodium chloride? Let us see this one. This is the crystal of sodium chloride. When it is heated in the vapor of sodium, then what happens? The sodium deposited over it. Clear? The deposition of sodium, I'm not going to show it over this lattice. I'm going to show it here. Why? Because if I draw the sodium metal here, then you will not able to see the phenomena which is occurring below it. It means it is like this. This one is the lattice. This one is the lattice. This one, lattice of NaCl. And what happened? When it is heated in the vapor of what? Sodium, then what happened? Sodium deposited over it. Clear? Then what happened? Then the chlorine Cl minus will diffuse, then this chlorine will diffuse out to the surface. What you see here? This chlorine will diffuse to the surface, and when it diffuses to the surface, then it will react with the sodium. Na. Here is Na, and here the chlorine diffuses to the surface. It means when sodium undergoes formation of Na plus electron, and this Na plus react with the diffused chlorine to the surface, it means Cl minus, and forms NaCl. What is left there?